Hey students, welcome to Sustainable Energy. I'm Rudi Schlaf, a professor at the Electrical Engineering Department at USF. This is part one of the solar energy segment. In part one we will discuss the physics of solar cells, we will discuss silicon solar cells and thin film solar cells. The first part of the solar energy segment focuses on photovoltaics. Photovoltaic devices are usually referred to as solar cells. And in solar cells, light from the sun is directly converted into electricity. This photo shows a typical array of such solar cells as they would be installed in a photovoltaic plant. The small dark squares that you see in these panels, they are individual silicon wafers that have been configured to work as solar cells. In these cells, photons that come from the sun are directly converted into electrostatic potential energy of electrons, and this enables these electrons to drive a current through a load that is connected to these panels. So what is going on inside these solar panels? Essentially, solar panels are generators that generate electricity. If you have a generator, then you usually have two terminals, a negative one and a positive one, and you could connect a load here, and then a current would flow through the load. So inside the generator, what we have is some type of device that takes electrons on one terminal in a low energy state and transports them up to a higher energy level on the other terminal. Because we have this energy difference between the two terminals, if we connect a load between the two terminals of the generator, the electrons will flow through the load from the higher energy side to the lower energy side of this generator. So in this type of diagram, the energy axis is the y-axis. So this is a low energy state and this is a high energy state. And you could actually think of the x-axis as a distance axis, because we really physically transport electrons from the low energy terminal to the high energy terminal. The units on the energy axis, these are electron volts. We encountered those already in the energy basics segment. And essentially 1 electron volt is the energy that an electron has if it is accelerated through a potential of 1 volt. So if we have a generator that gives them 1 electron volts of energy, this generator would just have a voltage of 1 volt. And so we could also think of the electrons as they go through the load, that they're actually traveling from one end to the other through a 1 volt potential drop. So they sort of, you could think of it like they're rolling down the hill. Now in a solar cell, such a generator is formed by a semiconductor material that just has energy states that can work as the low energy state and the high energy state. The energy that moves the electrons from the low to the high energy state, that comes from the photons, from the light that hits the solar cell. So a photon arrives from the sun, it strikes an electron on a low energy state, and then it shoots it up into a high energy state. What we also need in a solar cell is a mechanism that drives the high energy electrons on one end and keeps the low energy electrons on the other. So we again get a low energy end and a high energy end of the solar cell between which we can connect the load. If you want to understand the promises and issues of solar cells, we need to discuss semiconductors briefly. Semiconductors are covalently bonded materials. That means if you take two atoms and you put them together, they form a covalent bond in semiconductors, and the hallmark of covalent bonds is that the individual energy levels of the separated atoms, when they come together and form that bond, they form a lower lying bonding energy level and a higher lying anti-bonding energy level. And the electrons that were on the atomic energy levels, they go together onto the lower lying bonding energy level. And that creates that situation that we need in a solar cell, in a photon-based generator. We have a lower lying energy level that has electrons on it, and we have an empty energy level that is available for these electrons, so we can shoot them up there with photons. So this is just one molecule now made from two atoms. So two atomic energy states make two molecular energy states. So you see already that the number of energy states in a material corresponds to the number of atoms that we have in there. So consequently, if we put more atoms together and bond them covalently, then we get more bonding and anti-bonding states. So in this example, we took 8 atoms, and that means we get 8 bonding and 8 anti-bonding states. So you can imagine if we do this with an infinite number of atoms or close to infinite number of atoms, like in a silicon wafer or something of that nature, then we would get a very large number of anti-bonding and bonding states. So once we have a material like this, it is obvious that if we shoot photons in here that have an energy that is larger than the energy difference between the highest of the bonding and the lowest of the anti-bonding states, we can start moving electrons into a higher energy state, and that is the foundation for our generator. As I said, if we put many atoms together, make a solid state body out of them, then we get a whole bunch of bonding energy levels and anti-bonding energy levels. And in a macroscopic chunk of semiconductor, we call the bunch of anti-bonding levels the conduction band, and the bunch of bonding levels the valence band. So individual states became a band of states. So in the following, we'll just show these boxes representing these bunches of low energy and high energy states. The energy difference between the upper end of the valence band and the lower end of the conduction band, that is called the band gap, and that is typically symbolized with Eg. E gap, the energy of the gap. And this gap essentially determines the minimum photon energy that is needed to bring an electron from down here up here. All semiconductors have a specific band gap that is characteristic for the particular material. So when light hits such a semiconductor, and the energy of the light, here symbolized with this wavy green line, the energy of this photon is larger than the band gap, then an electron is moved from the valence band into the conduction band. And of course what that means is we have now one electron up here in the conduction band, but we also have a missing electron down here in the valence band. And this missing electron, that is called a hole. And if you think of it, there is now an atom that is lacking an electron, and of course this atom has now a positive charge, right? Because we have an equal number of protons in the nucleus of the atom as we have electrons surrounding it. And so this positive charge, that can be thought of as a positively charged particle in a sea of otherwise negative electrons around it in the valence band. In the following, we will actually treat these positive charges very similar to the electrons that are our negative charges. So if we would apply an electrical potential between this side and that side of the semiconductor, right? So we would, let's say, put the positive pole here and the negative pole here, then these positive charges, the holes, they would get drawn towards the negative pole, and the negative charges, the electrons, they would get pulled towards the positive pole. So in a semiconductor, we have essentially two types of charge carriers, positive ones named holes and negative ones the electrons. Both of them will contribute to the current that is flowing inside the solar cell. Once the electrons are generated in the conduction band and the holes in the valence band, we need to devise a mechanism that separates them. So the electrons need to go on one end and the holes need to go on the other end. That will allow us to pass a current of these high energetic electrons from this side through a load, and then they come back on the other side and recombine with one of these holes. This separation of electrons and holes can be achieved by a built-in potential gradient. So in essence, we tilt these bands in a way that electrons roll down the hill to one side, and the holes, because they always do the opposite of electrons because of their opposite charge, they will move uphill towards the other end of the solar cell. Such a built-in potential can be achieved by inserting positive and negative charges that are immobile within the solar cell. Such charges are ions, and they can be implanted with an ion implantation tool. Doping is the method to insert such stationary ionic charges into the semiconductor. There are two types of doping, N-type and P-type. And in N-type doping, we generate positive stationary charges, and at the same time we generate electrons in the conduction band. So the semiconductor actually becomes a little bit more conductive by putting in these arsenic atoms. P-type, on the other hand, we put something like boron into the semiconductor, and boron results in negative stationary charges, and we generate holes in the valence band. So the general idea of this doping process is to introduce impurities to the silicon lattice. So the blue atoms, these are silicon, and then we put an occasional arsenic atom into this silicon lattice. And if you look here at the snippet of the periodic system, arsenic is one column higher than silicon, so that means it has 5 valence electrons versus 4 of the silicon. That means this fifth valence electron, that doesn't really fit into this silicon lattice, because it is assumed that each of the atoms has 4 valence electrons that are participating in these 4 bonds around each silicon atom. So this fifth electron is a little bit like a fifth wheel on a car, and so it doesn't really participate in the bonding of the arsenic atom, and therefore it can very easily leave the arsenic and move through the crystal. And this of course means that the arsenic, because it has one more proton in the nucleus than silicon, it will become a positively charged arsenic ion, and a free electron is moving throughout the silicon crystal. And this is what you see here, right? We have the stationary arsenic that is bonded inside the silicon lattice, and one of the electrons is now a free electron that moves around in the conduction band. So this can participate in conducting a current. Now with p-type doping, a very similar thing happens. Just we need to go one column to the left of silicon. And of course here we have only 3 valence electrons, while silicon has 4. And so you can imagine what's happening if we put, instead of the arsenic, a boron atom in here. It cannot form one of the bonds because it has only 3 electrons. And so one of the bonds is broken, and that means that an electron that is available in the crystal can hop onto this broken bond and repair it. But that means, since the boron has 1 fewer proton than the silicons in its nucleus, that means that the boron is becoming negatively charged. And so we have this scenario. We have a negative charge that sits on the boron and it is stationary, and in the crystal we have a missing electron somewhere, and this is a hole. So this means, in summary, N-type doping allows us to create a situation where we have mobile electrons in the conduction band and positively charged arsenic atoms that are stationary in the crystal. And p-type doping creates the opposite. We get negative charges that are stationary within the crystal, and we have holes in the valence band that can move freely. So the potential gradient is essentially generated by putting a layer of N-type material on top of a layer of p-type material, because now we have positive charges on one side and negative charges on the other side, and so you get something similar to a capacitor which has an electrical field inside. This process is shown here. So to get that built-in potential that will help us separating the electrons and the holes in the solar cell, we make a p-n-junction. In practical terms, this means one uses an N-type silicon wafer that is all the way N-type doped throughout the entire volume, and then with an ion gun one shoots in p-type dopants. And so we have this situation. We have on one side n-type material, and then we have a layer of p-type material that has been generated by implantation. And so on the n-type side we have stationary positive charges and electrons that can move in the conduction band, and on the p-type side we have stationary negative charges and positive holes that can move throughout the p-type region. So if we bring these two in contact, what happens is, because the electrons can move on the n-type side, they repulse each other, and that means they distribute across the entire slab of material, n and p-type regions. This means that on the n-type side we have some stationary positive charges that are not compensated by negative charges. They are now over here on the n-type side. Now with the p-type material the exact same happens, just in the opposite direction. The holes are distributing throughout the entire material, and they leave behind some non-compensated negative charges. This means that this side here charges positively and the p-type side charges negatively. So we get this scenario. This here is the charge and this is the x-axis, and so we have positive charges at the interface in the n-type material and negative charges at the interface of the p-type material. This means we have something like a capacitor at the interface, and so there is an electrical field between positive and negative charges and an associated potential gradient. Now if we put electrons into this electrical field, into this potential, then the electrons will roll down the hill, so they will have a tendency to go over to the n-type side, while holes, they will float up, and so they have a tendency to go over to the p-type side. And this means if we generate electron-hole pairs with photons, the electrons are being pushed to the left and the holes are being pushed to the right, and we achieved our goal of separating the two. Here you see this concept applied to a solar cell. So solar cell essentially is just a p-n-junction with contacts on either side. Once a photon hits the solar cell, electron-hole pairs are generated. So we get the hole in the valence band and the electron in the conduction band. By the way, in such diagrams we show now the conduction band just as a simple line and the valence band also. So this is the valence band maximum and this is the conduction band minimum, and this here is the energy gap between them. Okay, so the photon hits, we get the electron-hole pair, and then because we have now our built-in potential, the electron is being pushed to the left and the hole is being pushed to the right, and that's great. So we have now electrons on this side and holes on that side, and the voltage of the solar cell at this point is of course the difference between the valence band maximum on this side and the conduction band minimum on this side, right? This is where the electrons are and this is where the holes are, and if we would connect a load now here, then the electrons would flow from this energy level to that energy level and catch themselves a hole and then recombine. This would close the electrical circuit. So if we put on the solar cell many photons, then of course we get many electron-hole pairs, and more electrons will drift over to the n-type side and more holes will drift onto the p-type side. And you can imagine the more holes and electrons we get, the original built-in voltage, this potential here, is being reduced, right? Because formerly we had positive charges here and negative charges here, but now they're compensated with these photon-generated electrons and holes. And so that means that the voltage increases that is on the solar cell, and that's what you would expect: more light, more voltage. The open circuit voltage is that voltage that develops if we put really a lot of photons on there. Then at some point this goes into saturation, right? Because this separating potential gets smaller and smaller in this process. It becomes less efficient to push the electrons here and the holes over here. And so at some point they will start spilling back over, and this is then the moment when this process stops. And at that point we have a maximum voltage here, and that is called the open circuit voltage. So what happens if we connect a load and extract a current from this solar cell? So as I just showed on the previous slide, in open circuit situation, at some point we get a steady state situation, and we get a maximum voltage that is on this solar cell. Once we connect the load now, the electrons flow through the load, and here they recombine with holes on the lower energy side of this solar cell. Now we have a race between the photons that come in and generate electron-hole pairs and the current that is permitted through the load. The current, of course, depends on the resistance of this load, and this load then performs some work or simply heats up. Now it's obvious what is happening. As we extract the current, we reduce the charge on the n-type side and the p-type side because we drive the electrons through the load, and here they recombine with holes, and thereby the number of holes is being reduced on this side. So out of a sudden, instead of many charges on either side, we only have a few. And that means, of course, that this open circuit voltage is being reduced. So a photovoltaic cell, a solar cell under load, has a voltage that is smaller than the open circuit voltage. In fact, this voltage, of course, you can imagine now, depends crucially on the resistance of the load. If we give the load a low resistance, we extract a lot of current, then of course this voltage here will be smaller because we remove more and more charges on either side of the solar cell. And if we use a load with a high resistance, then we will be closer to the open circuit voltage. So what we see here immediately is that the performance of a solar cell crucially depends on the load that is attached to it. Solar cell and load need to be matched to maximize the work or heat that can be extracted from the solar cell. This relationship between current and voltage of a solar cell is shown in this diagram in a more systematic way. This is a so-called current voltage diagram. On the y-axis we have the current, and on the x-axis we have the voltage. And in this quadrant, this is the active output region of the solar cell. The red curve, that gives us the relationship between the current and the voltage of the solar cell. This here is the point where we have the maximum output voltage, right? We get the largest voltage of the solar cell, but we have zero current. So this is the open circuit voltage, and that is the case where we have a minimized internal potential and a maximum output voltage of the solar cell. Now the other extreme is where we have maximum current but no voltage. This is the case where we essentially short circuit the solar cells or just connect a wire between the two terminals. In neither case we get any output power of the solar cell. If you remember, power is current times voltage. The unit is volt ampere or watt. It's obvious that we have to be somewhere in between these 2 points on the IV curve of the solar cell. The best point to operate the solar cell at, the voltage current combination, is that where we get a maximum area of that rectangle that is defined by that particular point on the IV curve of the solar cell. That means that we have to design our load in a way that it draws exactly this current at that particular voltage. So the bottom line here is, whenever you use solar cells, you need to match the load and the solar cell so that you are as close as possible to this maximum power rectangle. Now we understand how solar cells work in principle. Now I want to focus on issues to make solar cells as efficient as possible. Solar cells are an energy conversion device, and we know now that when you convert energy from one type into another, we always have some losses. Now it was calculated already in 1961 by Shockley and Queisser that for a single junction solar cell, and so that's the one that we just discussed, without concentrators, the efficiency is 31%. So we're losing 69% of the energy that's in the light, and we can only get 31% as electricity. Now this is the theoretical efficiency limit. It's clear that a practical implementation of solar cells is not as efficient. Current commercial designs are close to 20% efficient. Here is a list of some designs that are available. So amorphous silicone, here we are maybe at 8%. And the best ones here is a sun power WHT solar cell
that is close to 20. So you see that depending on the type of solar cell and the way they are manufactured, etc., there are vast variations in efficiency. It should be pointed out here that you have a more highly efficient solar cell, then you need to cover less area with the solar cell to get the power that you need. The main loss factors in solar cells are light reflection from the surface of the cell, so the photons don't even reach the semiconductor region in the solar cell. There is the difference between the band gap and the photon energy. In most cases, the photon energy is a little bit bigger than the band gap, and this energy difference is usually dissipated as heat in a solar cell and doesn't contribute to the electrical current that is flowing. And then we have the recombination of generated electrons and holes within the solar cell instead of only after going through the load. A significant part of the energy losses in solar cells is due to the mismatch between the band gap and the energy of the impinging photons. If the photon energy is larger than the band gap, e.g., then the difference of energy between the photon energy and the band gap, this difference here, that is dissipated as heat. So the electrons are being shot up to the conduction band, and then they, as they say, thermalize down to the conduction band minimum, and this is the level on which they participate in the photocurrent. So all this energy here is lost to heat that is dissipated to the environment. So it's crucial that in a solar cell the band gap is matched as good as possible to the energy of the photons that hit it. The problem now is, of course, to match the photons that are coming from the sun with the best solar cell energy gap. This here shows the spectrum of light that is coming from the sun, and this is now in electron volts. So the photon energy is shown in electron volts in this graph, and this here is the intensity, the power density on the surface per photon energy. And so we see here we have this fairly continuous spectrum composed of the infrared range at low photon energies and the ultraviolet range at higher photon energies, and in between we have the visible range here from red to blue. The gaps here, we know that now from the discussion of the greenhouse effect, these gaps come from the absorption in the atmosphere. The total energy that is in this solar spectrum on a clear day on the Earth's surface, that is about 1000 watts per square meter if the solar cell is perpendicular to the incidence of the sun. If you have a 20% efficient solar cell, you can get a maximum of 200 watts per square meter under ideal light conditions. So that means a clear sky and the sun is as high as possible. So what happens if we use a single junction solar cell, that is a solar cell that has only one semiconductor material with a particular band gap, to extract energy from sunlight? In this figure, this is shown at the example of silicon solar cells. Silicon solar cells are still the most ubiquitously used solar cells. And so silicon has a band gap of 1.12 electron volts. One can draw a line in this solar spectrum at 1.12 electron volts, and we can immediately say that all the photons that have a smaller energy than this band gap, they will not be absorbed at all, and so they are already lost to the energy conversion process right from the start. They simply go through the solar cell without being absorbed. The photons that have a higher energy, now we know that the higher the energy is in comparison to the band gap, the bigger the loss of energy that we have relative to the output. What remains essentially is the area under the orange curve. That is the energy that we can get out of the solar cell. If you compare this area under the orange curve with the area under the solar spectrum, then it is immediately obvious that a large part of this energy loss that was calculated by Shockley and Queisser comes from this phenomenon. It is obvious that with a single junction solar cell, one always has to make a compromise. No matter where you put the band gap of your solar cell, you will always have a part of the spectrum that is not absorbed, and the remaining part we have that heat loss because of the excess energy of the photons relative to the band gap. There is a way to reduce these losses, and that is by using a multi-junction solar cell that is composed of a number of semiconductor materials that have different band gaps that are matched to certain parts of the spectrum. With that, one can minimize the heat loss and thereby achieve a better efficiency. The price is, of course, a more complex design that is more expensive to manufacture. Another major part of energy losses in solar cells is the so-called recombination loss. This phenomenon reduces the number of electron-hole pairs before the electrons and holes can be separated and sent through the load. This is shown schematically here. First, we generate electron-hole pairs, and then there are several mechanisms that within the solar cell reduce the number of electron-hole pairs again. And of course, these electron-hole pairs then are lost to the electrical current that can be extracted. One mechanism is that they simply, because it takes too much time to separate them, they recombine. An electron finds a hole and then simply jumps back down into the valence band. And so we have a current that is flowing inside the solar cell, but of course it doesn't contribute to the current through the load. This type of process that can even re-release the photon back out of the solar cell. So it's almost something like reflection of the impinging light. Another mechanism is that the electrons find some states in the band gap. These states can be caused by impurities and defects of the material, and so they can jump on these states, and then when a hole comes by, they recombine with that hole. So it's a multi-step process. This step usually results in the generation of heat. Either way, these electron-hole pairs are lost and they cannot contribute to the electrical current that is extracted from the solar cell. Let's have a look at the principal design of solar cells. So essentially we have the semiconductor material that absorbs the light and separates the electron-hole pairs. Here in this example there is a p-type wafer that has been implanted with n-type dopants to create that p-n-junction here at this interface. The light is absorbed from above. There is an anti-reflection coating to maximize the number of photons that make it inside the semiconductor material. To extract the electrons, we also need contacts to the solar cells. On top, of course, this cannot be a layer of metal. This has to be a grid, because metal absorbs or reflects very effectively. On the back, on the other hand, we can have a continuous film. And so these two contacts now, they can be used to connect the load to the solar cell. Up to now, most solar cells are made from silicon. Here you see as an example a single crystalline silicon solar cell panel. So each of these squares is one silicon wafer that was transformed into a solar cell, and then these solar cells are connected in series across this panel. There are several reasons why silicon is so popular. One of the reasons is that there is a large industry that makes silicon wafers because of their applications in integrated circuits. So silicon manufacturing is very well understood. Another reason is that silicon is a very abundant material. In the crust of the Earth there are 27.27% silicon, and therefore one can expect that there will not be material shortages. The availability of the absorbing material is a big concern with solar cells. If large-scale implementation of solar energy is desired, then vast areas need to be covered with solar cells, and this requires a lot of material. This figure shows the principal sequence of processes that are needed to make silicon solar cells. We start out with sand, which is silicon oxide. And then in a coke reduction arc furnace, this silicon oxide is reduced to silicon, so that gives us metallurgical grade silicon. This process costs about 50 kilowatt hours per kilogram. Then we dissolve this silicon in hydrochloric acid. This makes chlorosilanes. Those we distill to high purity trichlorosilane, which then is reduced at 900 centigrades with hydrogen. This gives us polycrystalline silicon. This polycrystalline silicon is then melted at high heat, 1500 centigrades, and then a crystal is being pulled from that melt. This is called the Stokhalsky process. So that costs about 200 kilowatt hours per kilogram. Now we have a big silicon crystal. This is cut with a diamond saw into slices. This causes a 40% loss of the silicon material, similar to cutting wood, where you make wood dust. Here we make silicon dust. These wafers then are polished with a chemical mechanical polishing process. Then we need to dope them to make that p-n-Junction. Then we put the anti-reflection coating on there. Then we make the contacts, and then the solar cells are being assembled into a module and tested. So you see that a lot of energy is going into making solar cells in the first place, and this has the consequence that silicon solar cells, at least single crystalline solar cells, have an energy return on investment of only about 5. So this means if you have a 25-year lifetime, about 5 years are being used to simply pay back the energy that it costs to make the solar cells. This is a schematic of the arc furnace coke reduction process. Essentially, one has a submerged electrode and liquid silicon oxide mixed with some source of carbon. It can be coke or wood chips, coal, and as the silicon oxide is being heated with this carbon present, carbon dioxide and carbon monoxide forms and takes away the oxygen from the silicon, and that results in a relatively pure silicon melt at the end. So this process yields about 98% pure silicon. An issue, of course, with this process is that carbon dioxide is being emitted while making pure silicon. Let's look at a typical solar panel that is commercially available. This here is a module from Sharp. It has 235 watts and it's made from single crystalline solar cells. You see that here from these characteristic gaps between the individual cells, which is caused by the round shape of wafers. So we have 60 cells that are in series. The open circuit voltage is 37 volts. So you can calculate what comes out of each of the silicon cells. It's less than 1 volt. The maximum power voltage is 30 and the maximum power current is 7.84 amps. So if you multiply these two, you just arrive at about 235 watts. So you see here already that the wattage of a solar panel is given for that maximum power case. So if you can only achieve this by matching this solar panel with the right load that just draws this current if that voltage is applied. Here on the right is the IV curve of this solar panel. The current is on the y-axis and the voltage is on the x-axis. This is inverted relative to the schematic IV curve that I showed earlier. So this is the quadrant that earlier was shown in the lower right corner of the diagram. The interesting thing in this diagram is that they actually give 3 curves, and they are for different insolations, different levels of sunlight that hit the panel. The curve with the highest current, that is 1000 watts per square meter, so this is the blue sky perpendicular to the sun high up scenario, and then here we have 600 watts per square meter, which may correspond to a slightly cloudy situation. I drew in the maximum power rectangle. Here these are the 30 volts, and here you see the 7.84 amps. So this is maximum power at 1000 watts per square meter. It's interesting to see that the maximum power rectangle actually has slightly lower voltages if you go to lower insulation values. These curves are the power output curves, so here simply current and voltage are multiplied, and you see that the maximum of the power is there where the maximum power rectangle is drawn into the IV curve. So if you consider the efficiency of 14.4% of this panel and the output power, and knowing that we have 1000 watts per square meter of sunlight, then we can calculate the size of this panel, and the active area therefore is about 1.63 square meters. So far we only talked about single crystalline silicon solar cells. We know now that it costs a lot of energy to manufacture them, and it's also not a very streamlined manufacturing process because each of the wafers needs to be handled individually and then assembled into a panel and so forth. Thin film solar cells are a more recently developed variant of solar cells. There are many materials that are currently being investigated. Here on this graph we see a comparison between a few key materials. There is amorphous silicon. They have about an efficiency between 4 and 6%. Then there is microcrystalline silicon, which has about 8%. Cadmium telluride is similar, and then there is cadmium indium sulfide that is at about 10%. Thin film solar cells have many advantages because they reduce the amount of semiconductor used, especially direct bandgap materials like cadmium telluride or copper indium sulfide. The absorbing layer can be much thinner than in the case of silicon. That reduces the amount of material. Other advantages are that larger areas can be coated in reactors. That streamlines the production process. That makes thin film solar cells very promising candidates to reduce the energy and financial costs of solar cell manufacturing. Obvious disadvantages are that the efficiencies are lower than comparable single crystalline solar cells. This is caused by the higher defect rate in thin film materials, which increases recombination, and so one needs a larger area with thin film solar cells than with single crystalline solar cells for the same power. However, this is more than compensated by the considerably lower cost of thin film solar cells. This slide shows how amorphous silicon thin film solar cells are made. Amorphous silicon does not have an ordered crystal structure, so we have something that may look like this. It's more a chaotic arrangement of silicon atoms that are bonded to each other through a varying number of bonds, so it's a little bit similar to glass. The process uses a plasma reactor. It's a plasma-enhanced chemical vapor deposition, PECVD. In this process, a precursor gas, for the case of silicon, this is silane, silicon H4, mixed with helium. Helium is the carrier gas that also makes the process fairly safe because there's only a small part of silane in there, which is a fairly dangerous gas. This gas mixture is being put into the reactor, and then inside the reactor there are electrodes, and a plasma is being struck between the electrodes, and in that plasma the silane decomposes to silicon, and the silicon deposits on the substrate. The amorphous silicon film that forms on the substrate has many defects and therefore has poor electronic properties. These electronic properties can be improved by passivation with hydrogen gas. What happens there is that unsatisfied dangling bonds, as they're called, single electrons that are on the silicon atoms, are being passivated with that hydrogen. So the hydrogen bonds to the silicon, and that removes trap states within the band gap, so the electrons and the holes can travel further before they recombine. Despite such efforts, amorphous silicon solar cells have a much lower efficiency than single crystalline cells. It is quite a significant difference. Single crystalline cells can have up to 20%, while the amorphous silicon solar cells are only in the range of 6 to 8%. Aside from recombination, Another reason of the poorer efficiency is the larger band gap of amorphous silicon, which is 1.2 to 2 electron volts. And if you remember the slides about matching the band gap to the photon energy, then this here tells you that a larger percentage of the sunlight in the longer wavelength, lower energy range is not being absorbed by these cells, and therefore the efficiency is lower. The advantage of amorphous silicon clearly is that they're much cheaper, and also that it takes much less energy to make them, because the Stokhalsky process for making single crystal silicon is being omitted in this process. Amorphous silicon solar cells use a different device structure than their single crystalline cousins. Instead of a simple p-n-Junction that is sufficient in single crystalline material to separate the electrons and holes that are generated by the photons, in amorphous silicon we use this pin structure, where an intrinsic silicon layer is sandwiched in between n and p-type materials. The reason for this approach is that this intrinsic silicon film distributes the potential between the p and n-type layers over the entire absorption region of this solar cell. Therefore, the electrons and holes are being pulled by the electrical potential all the way until they reach the contacts. This improves the chances of the electrons and holes to make it without recombining. The other main difference is that in these amorphous thin film solar cells, a conducting oxide film is used as top electrode. It's made from tin oxide. The advantage of this approach is that the metal grid is avoided, so it's a much cheaper production process. Here we simply coat the substrate with another film on top of the silicon. The metal grid that requires patterning, and it also has the disadvantage that light is being absorbed in the metal grid that is not available for the electricity generation in the solar cell. The disadvantage of the conducting tin oxide film is that its conductivity is considerably lower than that of pure metals, and that generates an ohmic resistance in the top contact, which lowers the efficiency of the solar cell. The back contact of amorphous silicon solar cells is made from aluminum. That is the same with single crystalline materials. The reason for that is that aluminum is a material that makes a good ohmic contact with n-type silicon, and that leads to a low series resistance of the back contact. A more recently developed type of thin film solar cells are Chalcogenide-based cells. Chalcogenides are compound semiconductors composed of metals like copper, cadmium, indium, gallium in combination with chalcogenides such as sulfur, selenium, and tellurium. That gives us materials like cadmium telluride, copper indium selenide, copper indium sulfide, and so forth. The great advantage of these materials is that they have direct band gaps, which means that they can absorb photons much more efficiently. This means that the thickness of the semiconductor film can be much thinner than it would be required for silicon. This can be a factor 10 or even a factor 100 compared to the silicon. This means that much less material needs to be deposited, and that of course reduces cost. Another advantage is that these materials lead to solar cells that have a fairly high efficiency, at least for thin film solar cells. Efficiencies can be as high as 12% or so. Potential issues of these materials are that several of the elements used are fairly scarce. For example, tellurium, indium, and gallium have very limited supplies. In addition, cadmium poses an environmental risk because it is a heavy metal. This table is from an interesting study by Anderson from 2000. In this research study, it was estimated how much power could be installed in chalcogenide solar cells depending on the availability of each of the components in those compound semiconductors. And the interesting column is this here, SMC. That is the total power achievable for each technology if one particular material would run out, but the others are unlimited. So in the case of cadmium telluride solar cells, clearly the tellurium is the material that's in short supply. If it were only about cadmium, one could actually install 9 terawatt peak power. That would be sufficient to cover the total global electricity capacity of 4 terawatts. Unfortunately, there is much less tellurium around, 2 magnitudes less, and that means that only 0.3 terawatts peak could be installed in cadmium telluride solar cells. Obviously, there's enough cadmium to match the tellurium that is around. A similar scenario is for the copper indium gallium sulfide or selenide solar cells. Here the issue clearly is the indium, and based on the indium availability, only 0.09 terawatt peak could be installed. So both of these technologies are far from able to cover global electricity needs. It is clear that they can only be part of the solution. Here you see an example of a cadmium telluride module made by First Solar. The appearance is strikingly different from single crystalline silicon solar cells. It's just one black slab instead of these slices of single crystal wafer that are glued next to each other. I tried to calculate the efficiency of this panel. Somewhere on their website they gave the size of the FS277 model that is shown here. It has an area of 0.72 square meters. Based on the output power and assuming the standard 1000 watts per square meter insolation, we can calculate that this module puts out 107.6 watts per square meter, and that corresponds to an efficiency of almost 11%. It's interesting to compare the efficiency of solar panels with the efficiency that can be achieved when these panels are put into a photovoltaic power plant. In Germany, they built a pilot plant based on these First Solar cadmium telluride modules in Wald, Poland. They used an old airport and just covered it in these modules. And that's what you see here. This is a Google shot before. The initial stage of this plant was just to cover the area inside the red rectangle. This would be this part. What you see here is the most recent stage that they added to this power plant. My calculation now refers to the initial stage inside the red rectangle. This part of the plant has 40 megawatts peak. So that's about 1/25 of a major coal-fired or nuclear power plant. They typically have 1 gigawatt or so. So 1/25. This area actually is about half of USF's main campus in Tampa. Just to give you an idea how big this is. We can calculate now based on this area. I just measured it on this Google aerial photo. They give you a scale. So this is 900 meters, the red bar. And so I was able to calculate the area of this plant. So it comes out to about 2 kilometers by half a kilometer. And that is just about 1 million square meters. So if we divide the 40 megawatts, which is 40,000 kilowatts, by 1 million square meters, we end up at 0.037 kilowatt per square meter. So we have 1 kilowatt insolation. That means we get about 3.7% of the energy. Compare this efficiency to the initial almost 11% efficiency of the individual module. That means that a lot is lost because of plant infrastructure and the necessary spacing of the modules.
This concludes part 1 of the solar energy segment. Thanks for watching.